This is the session related to the unit bending moment and shear force. Previous sessions we have discussed few problems related to the cantilever beam and simply supported beam. Shear force diagram, we are going to draw the shear force diagram and bending moment diagram for the simply supported beam carrying in point load and UDL combination. Previous session simply supported beam carrying in point load separately and uniformly distributed load separately we are calculated. This session we will take the combination of both. What do you mean by shear force diagram? Shear force diagram is the diagram which shows the variation of shear force that we are already explained in previous sessions, and also bending moment diagram is the diagram which shows the variation of bending moment along the length of the beam. These are the sign conventions what we are adopting. Downward forces as in positive, upward forces as in negative. In simply supported beam, as discussed in previous session, reactions will be upward force, downward force whatever the loads acting, point load or uniformly distributed load, and then bending moment, clockwise movement we are considering as in negative, anti-clockwise movement considering as in positive. Let us take in one simple example which is having a beam, simply supported beam having a uniformly distributed load of 5 kN per meter for a distance of 3 meter from left support. Left support is A, and then one more point load which is acting at a distance of 1.5 meter from D, or it is acting at a distance of 1.5 meter from the right support B. Here what we can observe, this beam is having a combination of uniformly distributed load as well as point load. First, for simply supported beam we have to calculate reactions at the support A and support B. Let us call reaction at A as in RA and reaction at B as in RB. For calculating the reactions we have to apply the equilibrium condition, sigma MA is equal to 0. Moment about the A is equal to 0, one condition, and another condition is upward forces is equal to downward forces. Let us take moment about A, and also I explained previous session bending moment at A and B is 0 for simply supported beam. Now moment about the A, RB into 6, reaction at B is RB, and which is acting vertically upward, and this moment will be anti-clockwise direction. We are making an anti-clockwise direction is equal to clockwise direction, or sum of the moment about the A is equal to 0. RB into 6 is the distance, that is span given in the problem. RB into 6 which is anti-clockwise must be equal to this vertical point load 15 kilonewton into distance from the A to C. A to C distance is 3 meter plus 1.5 meter, that is 4.5 meter. 15 into 4.5, that is the moment due to 15 kilonewton point load, which is moment is in this direction, that is clockwise direction. Then one more uniformly distributed load as explained in previous session, 5 kilonewton per meter, that we have to convert into the equivalent point load. 5 into 3, that is 15 kilonewton. 5 into 3 is the 15 kilonewton, and distance where it acts, its center of this uniformly distributed load, that is A to D 3 meter. Center of this 3 meter, this uniformly distributed load acts, that is 3 divided by 2, 3 by 2, that is 1.5 meter from A. Therefore, moment due to uniformly distributed load is 5 kilonewton into 3, 15 kilonewton into 3 by 2. This is the moment due to uniformly distributed load, which is also clockwise moment. Now, if we simplify this, 90 kilonewton is the total moment, 90 kilonewton meter is the moment due to clockwise downward loads, and then support moment is RB into 6. Therefore, RB is equal to 15 kilonewton. Now we have the value of RB. To calculate RA, whatever the downward forces, downward force is 1 is 15 kilonewton, another load is 5 kilonewton per meter into 3, 15 kilonewton. 15 plus 15, 30 kilonewton is the downward load, and upward load RA plus RB. RA plus RB must be equal to, downward load is 5 into 3, 15 kilonewton, plus one more load is 15 kilonewton point load. Therefore, 30 kilonewton is the total downward load, that must be equal to RA plus RB. Therefore, RA is equal to this 30 minus RB. RB we have already 15 kilonewton. If we minus from 30, we will get 15 kilonewton as an RA. Therefore, RA is equal to 15 kilonewton, RB also 15 kilonewton. This is the values of support reactions at A and B. After calculating RA and RB, we can easily calculate the shear force for this given beam. Now we have the values: upward force RB 15 kilonewton, RA 15 kilonewton, and then downward forces, two forces are acting. Let us start from the B. Shear force at B point, shear force at B point is only one vertical force is acting, that is RB. We are considered as a minus 15 kilonewton, because upward force we are considered as a negative and downward force as a positive. Here 15 kilonewton is the shear force at B. Shear force at C, previous value minus 15 kilonewton, plus at C one downward point load 15 kilonewton is acting. Because it is downward, we are considered as in positive. Minus 15 plus 15, that is equal to 0 shear force at C. Next, move towards the D. Shear force at D, no further load is added between the D and C. Therefore, it remains same, 0 at D. Next, shear force at A. At A, whatever the right side forces acting, one is, previous value is 0 plus, that is 15 minus 15, 0 plus this 5 kilonewton per meter into 3, that is total load is 5 into 3, 15 kilonewton. You can observe whatever the 15 kilonewton what we have got here, that is same as RA value. Always whatever the shear force at left portion, that should be equal to RA value, right portion RB value. In between that, whatever the load is there, according to that we have to calculate. Next, bending moment calculation. Bending moment at B, as I already explained, bending moment at A and B is 0 for the simply supported beam. Bending moment at B is equal to 0. Bending moment at C, this C point we have to take the moment. Right side of the C, only one load is acting, that is RB into moment, which is anti-clockwise moment. That is why we can consider as an anti-clockwise movement as in positive, clockwise movement as in negative. 15 into 15 is RB value into distance is 1.5. From C to B is 1.5. How this is total span is 6 meter. 6 meter minus 3 minus 1.5. 4.5 if we minus, we will get the distance from C to B as 1.5. Therefore, 15 into 1.5 is the moment at C. This is the bending moment value at C, 22.5 kilonewton meter. Next, we will take the moment towards the D point. Then what are the forces acting right side of D? One is 15 kilonewton, one more is RB. RB will create an moment of anti-clockwise, and 15 kilonewton point load will have a moment of clockwise. Bending moment at D, 15 into 3, 15 is the RB value into distance from B to D. B to D distance is 3 meter, because A to D is 3 meter, balance is 3 meter, therefore moment is 15 into 3. Next one more point load 15 kilonewton, which is acting at a distance of 1.5 from the D. Therefore 15 into 1.5 is the moment due to point load. Here we are taken as in minus, because this 15 kilonewton creates produces the clockwise moment, that is why it is minus. Therefore value of bending moment at D is 22.5 kilonewton meter. Next bending moment at A is 0. We have the values at a salient points A, D, C, B. Let us draw the bending moment diagram. First draw horizontal line, and then first we will draw the shear force diagram, afterwards we will draw the bending moment diagram. First draw the horizontal line, and then here B shear force is 15 kilonewton, then it remains constant, and at C it is 0, and at D also 0. Then A it is 15 kilonewton. From A to D point we have to draw the inclined line, where uniformly distributed load is there. That point shear force diagram will be inclined line. Then close the polygon. This is the shear force diagram for given beam. What you can observe here, wherever point load is there, that place drop is there, and also at reactions, support reactions, it is drop. That means point load places there will be drop equivalent to the value of load, and then where uniformly distributed load is there, that portion it is sloping line. For drawing the bending moment diagram, first draw the horizontal line and mark the salient point, that is C point. Project the C point and mark the value of bending moment, and then D point also mark the value of bending moment, and then join from C to B, which is inclined line, and then A to D it is parabolic, because uniformly distributed load it is parabolic, and then D to C bending moment is constant. These are the two values where we are getting a maximum bending moment, that is at D as well as C, since shear force is 0 at these 2 points. This is the bending moment diagram. Now let us consider one more beam. In this case I have taken uniformly distributed load right half of the beam, and point load is acting at a distance of 1.5 meter from the support A. In this case again we have to calculate the reactions at A as well as B. To calculate the reactions at A and B, we have to take the moment about A. Clockwise moment RB into 6, reaction at B into, this is the moment towards the A, that is distance is 6 meter, RB into 6 is equal to 5 into, here we have to observe 5 into 3 is the load, 5 into 3 is the load, uniformly distributed load 15 kilonewton, into distance. In this case this load will act at center of 3 meter, that is 1.5 meter, 1.5 meter from C or 1.5 meter from B. To calculate the distance from the A point to this point, A point to center of the CB, from A to C is 3 meter plus 3 divided by 2, that is center of the CB, 3 plus 3 by 2. We have to calculate the distance from the center of UDL to the point where we read the moment. Therefore 3 plus 3 divided by 2. 5 into 3 is the load 15 kilonewton, into distance of UDL from the A is 3 plus 3 divided by 2. Then next load is 2 kilonewton, which is acting at a distance of 1.5 meter from A. Therefore 2 into 1.5. We have taken the moment of uniformly distributed load as well as the point load. Previous problem, uniformly distributed load was acting from A to C, that is why we are considered the distance from A to C, that is midpoint, whereas here uniformly distributed load is acting right half of the portion, that is why we have calculated from A to center point of uniformly distributed load. Now moment due to load is 70.5 and moment due to reaction is RB into 6. Therefore, RB is equal to 11.75 kilonewton. Now next we will apply the equilibrium condition, that is downward forces is equal to upward force. Downward force is 2 kilonewton plus 5 into 3, 15 kilonewton. 5 into 3 is the 15 kilonewton plus 2, that is 17 kilonewton is the total downward forces. Upward force is RA plus RB. We have already RB value. RB value is 11.75. 17 minus 11.75, that is 5.25 kilonewton is the reaction at A. For simply supported beam, always you should calculate the reactions at A and B before calculating the shear force and bending moment diagram. This is the RA value 5.25 kilonewton, RB value is 11.75 kilonewton. By having a value of RA and RB, we can easily calculate the shear force values. Shear force at B. B upward force is acting, that is 11.75, that is RB value. Therefore, shear force at B is equal to minus 11.75. Shear force at C. At C there are the two loads are there. One is 5 kilonewton per meter is the uniformly distributed load and one more load is RB value. First we will take the previous value, that is RB value as in minus 11.75 plus uniformly distributed load is 5 kilonewton per meter into 3, 15 kilonewton is the value of uniformly distributed load, minus 11.75 plus 5 into 3, that is plus 3.25 kilonewton is the shear force at C. Now move towards the D, shear force at D. Shear force at D is equal to previous value plus 3.25 plus one more point load is added here, that is 2 kilonewton. Then shear force at D is equal to 5.25 kilonewton. 3.25 plus 2 is equal to 5.25 kilonewton. We are using the plus value because it is a downward force. Then shear force at A should be equal to 5.25 kilonewton. Because from D to A no load is added, therefore shear force remains constant 5.25 kilonewton. This is the values of shear force at B, C, D and A. Next let us calculate the bending moment. We have the reactions at RA and RB as well as downward loads are there, 5 kilonewton per meter uniformly distributed load, point load is 2 kilonewton. Let us take a moment at each point. First bending moment at B is 0, bending moment at B as well as A is 0 for simply supported beam. Bending moment at C, C point, this C point right side of the C there are two loads are there, one is 5 kilonewton, one more load is RB value. Okay, 11.75 is the load into distance from C to B is 3 meter. 11.75 into 3, that is anti-clockwise movement, that is why it is considered as an positive. Next minus, because of load it will create an clockwise movement. 5 into 3 is the 5 kilonewton into 3 is the total load which acts at a center of 3 meter, that is 3 divided by 2, that is distance from C to load, that is center point of the load is 1.5, that is 3 divided by 2, 5 into 3 into 3 by 2. Therefore bending moment at C is equal to 12.75 kilonewton meter. Next bending moment at D. bending moment at D, we have to take the load, moment of loads for right side of the section, or we can take the moment left of the section. We will get same value. If we take moment left, that is RA into distance 1.5, we will get same value whatever the calculating from right side, that is RB into distance, RB into distance from D to B, and 5 into 3 is the 15 kilonewton from distance from the center of this point to the uniformly distributed load to the D point. See, 11.575 is the RB value. RB value is 11.75 into distance from D to B. D to B distance is 4.5. 11.75 into 4.5 is the moment due to reaction minus 5 kilonewton per meter into 3. 5 into 3 is the 15 kilonewton. Distance from the center of this uniformly distributed load to D, that is 3 by 2 is the center of uniformly distributed load, plus distance from D to C is 1.5. You can observe here 6 minus 3, that we will get 3 meter, minus 1.5, we will get the distance between the D to C is 1.5. 1.5 plus half of the distance, 3 divided by 2, that is the value for distance from the D to center point, that is 1.5 plus 1.5, 3 meter, 3 into 15. Okay, this is the moment about the D, 7.88 kilonewton meter. Bending moment at A is equal to 0. You can observe what I explained. We can take the moment from RA into distance. RA is 5.25 into 1.25. If you multiply, you will get the 7.88 kilonewton meter. Same value. Now, let us draw the shear force and bending moment diagram. First, draw the horizontal line and then drop negative value which is equal to the RB, this portion, and then here positive value equal to the RA, and then see here RA to C is, from A to C is horizontal, no shear force is constant, and then this point it is vertical drop equivalent to 2 kilonewton, and then again it is remains the constant, and this side it is equivalent to the RB value. From D to B we are drawing with the inclined line, because this portion it is uniformly distributed load is acting, that is why it is inclined. What we can observe here, one particular point where shear force changes from the negative to positive. Where shear force changes its sign, that a place maximum bending moment occurs. See, this is 5.25, here it is suddenly drops to 3.25, it is equivalent to the 2 kilonewton drop, and then here drop to this 11.75, in between that shear force changes its sign. This point we have to determine to calculate the maximum bending moment. For drawing the bending moment diagram, first mark the values at D and at C, and A it is 0, B it is 0, but this is the point where maximum bending moment occurs, this particular point, that we have to calculate afterwards. Okay, this portion, when we are drawing the bending moment diagram, you can observe here A to C it is the inclined line, and C to D is inclined line. From D to B is parabolic line. It is parabolic line with rising at this particular point, this point, because it is where maximum bending moment occurs. Okay, let us calculate the maximum bending moment point. Let us say this place where shear force changes its sign at a distance of x from the B. From B point we are measuring x in x value, that is the place where shear force changes its sign. We will have to calculate the x value. and balance. This balance portion will be 3 minus x, because total distance from C to B is 3 meter. Therefore, from C to B is 3 meter. We are called this point as an x. Balance value will be 3 minus x. To calculate the x value, we will consider as in two similar triangles. 3 minus x divided by this value, shear force value 3.25, must be equal to the x divided by 11.75. Value of this distance 3 minus x divided by the shear force value 3.25 must be equal to the x divided by 11.25, right side shear force value. If we simplify this, we will get an x value as a 2.34. By cross multiplication, we will get the x value as a 2.34. Therefore, x will be occurs, this shear force will occurs, will be 0 at a distance of 2.5 meter from the B. Now we have the value of 2.34. We have the point O, which is at a distance of 2.34 from the B. From the B, it is distance is 2.34. This place maximum bending moment occurs. To calculate the maximum bending moment at O, we have to take the moment about the O. That is one RB value is 11.75 into distance is 2.34. RB into distance at up to the O point 2.34 minus due to load, moment due to load is 5 kilonewton, 5 into distance is 2.34. We have to consider a load up to the 2.34 only. Therefore, 5 kilonewton into 2.34, that is the total load, into distance where it acts, center of the 2.34. 2.34 divided by 2. We should not take the 3 meter, 5 into 3. 5 into 3 means total load up to the distance of 3 meter. For 2.34 means only up to distance of 2.34 distance. 5 into 2.34 is the load and it acts at the center of the 2.34. That is 2.34 divided by 2. This is the maximum bending moment 13.80. You can see here 12.75, 7.88 C at D, but whereas at the O point we are getting in maximum bending moment as in 13.8, then it will drops 0 at the B. This is the portion where we will get the maximum bending moment. Okay, the previous problem we considered the one single point load with uniformly distributed load. In this case, I am considering the 2 point loads and one uniformly distributed load. That also this point load acts at the end of the uniformly distributed load. You should be very careful when point load meets the uniformly distributed load for calculating the shear force. I will explain that when we are drawing the shear force diagram. What we have to do first for simply supported beam, we have to calculate the reactions at the A and B. To calculate the reactions, we have to take the moment about A or moment about B, and then upward forces is equal to downward forces. We will get the RA and RB. Let us take the moment about the A. RB into 6. RB is the value at right support, with into distance is, it is anti-clockwise, distance is 6 meter. RB into 6 meter span is equal to anti-clockwise moment is equal to clockwise moment. Clockwise moment is one load is 5 kilonewton per meter, which is act at the center of this C to B, into distance is from center point to A point. 5 into 3 is the load, 5 into 3 is the 15 kilonewton load, and distance is A to C is 3 meter, because the 6 meter span, out of which 3 meter is the UDL is acting, balance is 3 meter, 3 plus, it acts at the center of CB, that is 3 divided by 2. We have to take the distance from the center of UDL to the point where we require the moment. 3 plus 3 divided by 2, 5 into 3 into 3 plus 3 divided by 2. This is the moment due to uniformly distributed load. Next is point load 5 kilonewton, which is acting at a distance of 3 meter from A. A to C distance is 3 meter. 5 into 3, distance 3 meter. This is the moment due to 5 kilonewton load. Then one more point load 4 kilonewton. 4 into distance from A to D is 1.5 meter. 1.5 meter. Therefore 4 into 1.5. This is the total moment at A. Then if you simplify, RB is equal to 14.75 kilonewton. Next, to calculate the reactions at A, downward forces. What are the downward forces acting? One is 5 kilonewton per meter. 5 into 3, 15 kilonewton, plus 5 kilonewton plus 4 kilonewton. 15 plus 5, 20 plus 4. 24 kilonewton is downward forces acting. Upward forces is RA plus RB. RA plus RB is equal to 5 into 3 plus 5 plus 4, that is 24 kilonewton. Therefore, RA is equal to 24 minus 14.75. This is the value of a 9.25 kilonewton is the value of RA. We have the values of RA and RB. By having in reactions and load, we can easily calculate the shear force and bending moment. These are the values RA and RB. Let us calculate the shear force. Shear force at B is RB value minus, because it is a upward force, minus 14.75 kilonewton is the shear force at B. Shear force at C minus 14.75 is the previous value, plus C 5 kilonewton per meter into 3, 5 into 3, plus one point load is there, that is 5. Total is plus 5.25 kilonewton. You can observe here B, it is minus 14.75 and it changes to plus 5.25. In between C to B there is a change of shear force. It is a negative to positive. Then shear force at D, no load in between the D to C, but at D one point load is there, 5.25 previous value plus 4 kilonewton, that is 9.25 kilonewton is the shear force at D. Shear force at D, no load is added between the C to D, therefore shear force at A is also equal to the 9.25, that is equal to the RA value. 9.25 kilonewton plus value for at shear force at A. Like this we have to calculate the shear force. To calculate bending moment, again we have the reactions RA and RB as well as loading system given. Bending moment at B is 0 for simply supported beam, A also 0. Bending moment at C point, what are the loads acting right side of the C? One is 5 kilonewton per meter and one more load is RB value 14.75. 14.75 will be having a moment of anti-clockwise. This UD will have a moment of clockwise. That is why we can consider this moment due to RB is a positive and moment due to loads as a negative. 14.75 is the load, RB value into distance from C to B is 3 meter. 3 meter is the distance. 14.75 into 3, which is anti-clockwise moment, and then 5 into 3 is the load, 15 kilonewton, and distance of this load is from the C is center of this load 1.5, 3 divided by 2. 5 into 3 into 3 by 2 is the moment due to uniformly distributed load. Therefore, total moment at C is 21.75 kilonewton meter. For calculating the moment at D, we can calculate two ways. Right side D right side whatever the loads are there, or D left side load is only one load is there, 9.25 into distance 1.5, you will get the moment at D. Let us take from right side, RB value 14.75 into distance from B to D is 4.5, 3 plus 1.5, 3 plus 1.5 is 4.5, 14.75 into 4.5 minus, this is 5 kilonewton into 3, 5 into 3 is the 15 kilonewton into distance is 1.5 from D to C, 1.5 from D to C plus center of C to B, that is 3 divided by 2, 3 divided by 2 plus 1.5, that is the distance of uniformly distributed load from D, minus one more load is there, that is 4 kilonewton, 5 kilonewton, one more load is there, that is 5 kilonewton into distance from D to C is 1.5, 5 into 1.5. Therefore, total moment at D is 13.88 kilonewton meter. We have to take the moment of 5 kilonewton, moment of 5 kilonewton per meter and moment of RB. That is force into distance up to the D point. And then bending moment at A is equal to 0. This is the bending moment values for this particular beam. Let us draw the shear force and bending moment diagram. This is the shear force diagram. What you can observe here, this is RB value, shear force at B negative, shear force at A positive, this vertical drop at A and vertical line at the A as well as B, and then it is constant from C to D, and then you can observe here it is a drop. What is the value of this drop? 9.25, and this drop should be equal to the 4 kilonewton. 9.25 minus 4, that is 5.25. You have to mark the point of 5.25 at C and 9.25 at this point, and there should be drop equal to the 4 kilonewton. Again here drop, this drop should be equal to the 5 kilonewton. I explained all the previous sessions also, this drop should be equal to the point load. This drop should be equal to the point load. Therefore, we have calculated 5.25 as the shear force at C. Then here you should not join the point from here to here sloping line. It's a mistake. This because here point load is acting, that equal to that point load you have to give a drop equal to 5 kilonewton, that is 0.25 is the value, you have to mark the 0.25, then from that 0.25 to B, this end we have to draw inclined line. If we draw directly from here to here, then we are not considered this point load. Okay, that is why always wherever the point load is there, that place equivalent to that point load magnitude, we have to draw a vertical line. Okay, this is the point where shear force changes its sign. Let us we can call it as an O point. We have to find the maximum bending moment where shear force changes its sign. This is the bending moment diagram. You can observe here from A to D point it is an inclined line, and D to C point it is an inclined line, and then from here to C to B it's a parabolic line, and this portion is rising because here we will get the maximum bending moment. We have to find the point where shear force changes its sign and then calculate the maximum bending moment value. Let us calculate the distance where shear force changes its sign. We can call this point where shear force changes its sign as a O, and distance from this O point to the O point to B as a X. and the distance from the C to the O point as an 3 minus x. 3 minus x divided by the 3 minus x is the distance from this point to the C point to the 0 O point, that is 3 minus x divided by the 0.25 shear force value is equal to x divided by 14.75. Therefore, x is equal to, if we carry out the cross multiplication, x is equal to 2.95. It is acting, this shear force changes its sign at a distance of 2.95 from the B point. We have the x value, we can calculate the bending moment at O. O point is the distance of 2.95 from B. 14.75 is the RB value into distance is x value 2.95. We are taking a moment up to O point, that is 2.95 distance, minus is, this is a clockwise movement due to the uniformly distributed load, minus 5 into up to distance 2.95. We have to consider the uniformly distributed load up to the 2.95 only. 5 into 2.95 is the load, and which acts center of the 2.95, that is 2.95 divided by 2. Okay, this is the moment about the O. Therefore, maximum bending moment at O is 21.75 kilonewton meter. This is the maximum bending moment value, where we can see the rise of the curve. We have to rise the curve at the point and then join the B point. This is the bending moment diagram for the given loading system. Now we will consider one more drawing, one more beam which is having an uniformly distributed load in between the 2 point loads. One point load is acting left side and right side 10 kilonewton, left side 10 kilonewton, and the central load is 5 kilonewton per meter. What you can observe here, see, A to B distance is 6 meter, and from A to the first point load is 1.5 and second point load is 4.5. Therefore, distance between the second point load to B is 1.5 meter. What we can observe here, this is the symmetrically loaded beam. 10 kilonewton which is acting at a distance of 1.5 meter from left support as well as right support, and central uniformly distributed load of 5 kilonewton per meter. Since it is a symmetrically loaded, we can easily calculate the reactions at A and B. How to calculate the reaction at A and B? Whatever the total load acting downward divided by 2, we will get the reactions at A and B. If it is a symmetrically loaded, you can without taking in any moment, just you can divide the total load, you will get the reactions at the A and B. What I am using the formula, where I am using the equilibrium condition, sum of the downward forces is equal to sum of the upward forces. Sum of the upward force is RA plus RB. Downward force is 5 into 3 is the uniformly distributed load equivalent to point load, 5 into 3 plus 10 plus 10. 35 kilonewton is acting downward. Upward is RA and RB. Since RA is equal to RB, because symmetrical loading, RA is equal to RB, 35 divided by 2, that is 17.5 kilonewton is the reactions at A as well as B. Okay, let us call these 2 points as in C and D, where point loads are acting. RA is 17.5, RB also 17.5. Shear force at B 17.5 kilonewton minus 17.5 kilonewton because it is a upward. Shear force at C for this 17.5 kilonewton, 10 kilonewton is added, which is downward. We are considering as in positive. Minus 7.5 kilonewton is the shear force at C. shear force at D, right side of the D, minus 7.5 is the previous value, plus uniformly distributed load is added, 5 into 3, 15 kilonewton, plus one more point load is added, 10 kilonewton. Therefore, 17.5 kilonewton is the shear force at D. And D to A, no load is added, therefore it remains 17.5 kilonewton, which is equal to the RA value. Okay, this is the simple calculation of a shear force. Next, bending moment. Bending moment at B 0. Bending moment at C, load is RB value 17.5, which is anti-clockwise movement, that is why positive. 17.5 into distance from C to B is the 1.5. 1.5 is the distance. Therefore, 26.25 kilonewton meter is the bending moment at C. Bending moment at D, we can calculate bending moment at D RA into distance, which is also equal to the right side loads, moment due to right side loads. 17.5 is the load, RB value, into distance from the D to B is 4.5, 3 plus 1.5 distance, that is 4.5, minus 10 kilonewton into distance from the D to C is 3 meter, 10 into 3. Then uniformly distributed load 5 kilonewton, 5 into 3, 5 kilonewton per meter into 3, 15 into distance which acts at the center of this distance 3 meter, that is 3 divided by 2. That is uniformly distributed load acts at center, from center to the distance from D is 1.5, 3 divided by 2, therefore 26.25. Even you can calculate the bending moment at D by RA into 1.5. RA into 1.5 is equal to 26.25 itself. Bending moment at A is equal to 0. Okay, this is the values of bending moment. Let us draw the shear force and bending moment diagram. See, this is the shear force diagram. First draw the horizontal line and then drop 17.5, left side 17.5 drop, and then it remains constant, and right side also it remains constant. Then you should not join these points. You have to draw the line vertical drop which is equal to the 10 kilonewton. 17 minus 10 is 7.5. Similarly, this side also, this 17 is the value at this point, and 17 minus 10 is 7.5. First you have to show the drop in shear force diagram equal to the point load, that is 10 kilonewton, and then join 2 points. That is where you have shown the drop, that from drop point to C point. Okay, you will get the shear force diagram. And also you can observe here, shear force, it changes its sign exactly at the center, because it is a symmetrical loading and a uniformly distributed load is acting at exactly at the center. This it changes its sign at the center. And to draw the bending moment diagram, first draw the horizontal line and mark the 2 points, that is 26.25 at D and C, and then draw the inclined line from A to D as well as B to C. In between the D to C, it is uniformly distributed load, that is why it is the parabolic curve. For shear force diagram, uniformly distributed load, inclined line. For bending moment diagram, it is a parabolic curve, and has shown as in rising the central point, because there we will get the maximum bending moment. Okay, to calculate the maximum bending moment at mid span, we are taking the moment about the moment at the center. 17.25 is the RB value into distance from center point to the B, which is 3 meter, minus load 10 kilonewton into distance center point to the C is 1.5, 3 divided by 2 is the 1.5, minus uniformly distributed load 5 into half section only we are considering. Load half, right of the half is 5 into 1.5 distance only. We are not considering the left side of the load, only half portion is 1.5 distance uniformly distributed load. Into that acts at the center of half portion, that is 1.5 divided by 2. 31.88 is the maximum bending moment at the center. 31.88. Like this we can calculate when it is symmetrically load is given, we can easily calculate the bending moment and shear force diagram. Okay, now this problem, another problem in this, I have considered the 5 kilonewton per meter acting throughout its length, 6 meter full length, as well as one point load at the center. You can see here, because this is also symmetrical loading, RA plus RB must be equal to the total load 10 kilonewton plus 5 into 3, 5 into 5 kilonewton per meter. We can consider the total load. Okay, then half of the load is 12.5 kilonewton. kilonewton is the reactions at the support. Then see shear force at B, which is equal to the RB value. Shear force at C. Shear force at C is the center point. Whatever the RB value plus minus for 12.5 plus this 5 kilonewton per meter into 3 meter, up to 3 meter we are considering right side only, plus 10 kilonewton at the center value. Shear force at A is equal to 12.5, which is equal to the RA value. Bending moment at B is 0, and then bending moment at C, center point, you have to take the moment, and bending moment at A is equal to 0. This is the shear force and bending moment diagram. What you can observe here, central point, it is changing its sign from negative to positive, and also you can observe here we have to drop, we have to keep a given drop of equal to the 10 kilonewton. Right side it is a drop of 12.5, left side drop of 12.5, center it is change of sign. Here entire diagram is a parabolic with rise at the center point, that is equal to the 21.25 kilonewton meter. In this problem I have considered 2 point loads, 1 kilonewton and 3 kilonewton 2 point loads, as well as one uniformly distributed load. As usual, we have to take the moment about the A for all the loads, 3 kilonewton into distance 5.5, 1 kilonewton into distance 4.5, 2 kilonewton into distance 2.5 is the distance of uniformly distributed load. You have to calculate the distance up to which uniformly distributed load is acting, and then distance of this uniformly distributed load to the left support. Then we will get the RB value is 5.79, and then RA plus RB must be equal to the total load. Total load is 3 kilonewton plus 1 kilonewton plus 2 into 2.5 distance it is acting, 9 kilonewton. These are the RA and RB value. Then calculate the shear force at salient points B, C, D and E, F. Then similarly you can calculate the bending moment at B is equal to 0, bending moment at C, whatever the load into distance. After calculating the bending moment and shear force, you can draw the shear force diagram and bending moment diagram. Here you can observe here, wherever the point load is there, there is drop, and where uniformly distributed load is there, there is inclined line, then it is horizontal line, and also you can see the bending moment diagram, it is inclined line. Parabolic line in between the where the uniformly distributed load is there, and further it is the inclined line. Then you have to calculate the x value. After calculating x, you can calculate the maximum bending moment at a point where it changes its sign. Okay, you can take the moment at from the right or the left, we will get the same value. This is the maximum bending moment, 7.36. Thank you. Okay, we will discuss the overhanging beam in next session. Thank you.